Bismillahirrahmanirrahim. Now I'm going to talk about the design of the helical compression spring under dynamic loading case, and I'm taking this as the first example, and this is a fatigue design problem. So let's read the problem. What is the problem? The problem is that we have a music wire. So now the wire type material is given. Music wire means what kind of material we have? ASTM A228. What I need? Infinite life. So n is greater than 10 raised to the power 6 cycles. It means we need endurance strength. And since it is a pure shear problem, we need endurance strength in shear, or it is called as SSE. These either ES or SE. There is a dynamic load which varies from 20 Newton to 80 Newton. So in other words, if I just look at my load, this is my force. So the maximum to the minimum. The maximum load is 80 and the minimum load is 20 Newton. That's what it means. The end deflection of the spring under the given dynamic load is 12 to 50 mm. What it means, at this particular load, the Y is 12 mm, and at this particular load, Y is 50 mm. And it's working at 5 Hertz. So what I have been given is the applied low frequency, which is 5 Hertz. And I have to check against the fundamental frequency of the spring for this one also. Because of the assembly consideration, the shut length of the spring cannot exceed 25 mm. So LS has to be less than 25 mm. And the free length cannot be more than 100 mm. So LO has to be less than 100 mm. And one other condition which is given, the manufacturer has only these size of the wires. So he has 1, 2, 3, 4, 5, 6, 7, 8. So 8 different types of spring wires are available. And these are my design constraints, which are below here. Having known these things, let me go to the next slide, tell you the fundamental difference between designing a spring against static load versus the dynamic load. So when we have the dynamic fatigue case, we know that my force goes from an alternating, and I have a mean component of the stress, of the force. In other words, my torsional shear stress will also be 2. One, I will have a shear stress alternate, and one I have the shear stress which is mean. Equation, this is equal to KB 8F, and this is alternate load, mean coil diameter divided by pi d cube. This is the formula that we have for the stress. When it want to calculate for the mean, then it will be the same. The only difference will come, it's same as 8. This will be the mean load. This is the mean coil diameter over pi, and this is the wire diameter. So here we are calculating two different stress. One is alternating and one is mean stress. The other stress we calculate is the shut stress. That's the stress at shut. Same equation, but preferably we use here the shear correction factor 8, the shut force D divided by pi dq. That's about the stresses. Now about the strength. What about the strength? What we need? We need the endurance strength. In shear, which means I need SSE. That's what I need. So if we use the Zimmerli data, which is on page 528 of your book. Sorry, let me go and I need to erase this because I have written the wrong values. So I'll go and back to the pen. 528, page 528. You will find over there the value for the alternate shearing stress, SSA, and mean shear stress. These are given for two different types of cases: peened, and you know already about it, and unpeened. This will have the lower values and this will have the higher values. This is better, but it will cost more money. And unpeened is definitely the cheaper. This is the cheaper one. Now I have few choices. Once I can say that use the Sainz-Zimmerli data, where SSM is ignored, and you only work with the SSA. The other is that now you go and you say, okay, I'm going to use the criteria from chapter 6. So for example, if I use the modified Goodman criteria, then what equation do I have? The modified Goodman criteria, it has the equation. I am going to write it in the shear form. SSA divided by SSE plus SSM divided by SUT is equal to 1. And you can see that this SSA goes here, this SSM goes here, SUT you calculate by A over D raised to the power M, right? And it has to change to SUS because this is shear. Actually, You get SUT from there and you calculate SUS, which is 0.67 of SUT. If you substitute all, what you can get? You will get from here the value of SSE. And that's what you need to compare with the in the analysis analysis to make sure that the factor of safety is above 1. So bottom line is this one that we need to. If I have a Gerber criteria, then what will happen? My equation will change. What is the equation? This equation becomes SSA over SSE and SSM over SUS square is equal to 1. That's based on the Gerber. And these values, these equations are given, what I have written here, this or this, they are given on page 315 in your book. Once we know these, now we can go to the, and we'll see. The procedure becomes very simple. So first I'm going to put the design constraint. We already said this is one of the design constraint. This is the other design constraint. The other design constraint that we have is this one. That's frequency, right? And I want this frequency, my applied frequency is 5 Hertz. And I know my fundamental frequency should be 15 to 20 times of F applied. So I will use the larger number, 20 times 5, that becomes 100 Hertz. That's the value that I want. I know the generalized design constraints, which are coming from the static case also: spring index, active coil, critical length, and factor of safety, etc. I'm going to assume unpeened material because it is cheap. I'm going to use as wound because it is cheap. I will assume a square and ground end conditions, which means the total number of coil is the active coil plus 2. And I'm going to use the robust linearity. So the C is 0.15, and I'm going to use the NF is equal to 1 based on Sainz-Zimmerli criteria. Remember, which ignores this one. What is given to me is ASTM A28. So I go to the table 10.4 and I know this is A, this is M, this is E, and this is G, and this is E. Also, what I know that at minimum force, this is the deflection. At maximum force, this is the deflection. And what I need to find out is spring wire diameter. That satisfies all constraints which are here and here, and all assumptions which are here. Then what I need to do, find all other spring parameters. So, and see, we'll start the calculation. If you remember that the spring wire size diameters that are available, it starts from 1.7 and it goes up to 2.8 millimeter. So I had chosen the maximum one. You can choose the smaller one because we have to do the calculation for each one of them. 1.7, 1.8, 2.0, 2.15, and so on. All the wire diameters that are given in the question. Since I know A and M and I know the wire diameter, this is my ultimate tensile strength and this is my ultimate shear strength, which is 67% of SUT. And I can calculate the yield strength in shear, which is from table 10.6, and I have taken over here the cheapest basically before set removed, not after set removed. So these are simple to calculate. My alternating force is what it is equal to F maximum minus F minimum by 2, and my the mean force is F maximum plus F minimum by 2. So I got F alternate and I got F mean. We can find out the spring rate, which is change in force divided by change in deflection. Change in force is this, change in deflection is this. So this is my spring rate. Now I will go and calculate the stress. But to calculate the stress, what I need D. And D is equal to C times D. I know this one. So I need to calculate C. And in order to calculate C, if you recall, this is the formula that was given in figure 10.3. And this is the equation for alpha. This is the equation for beta. I will calculate those and I will put it here. But be careful here. Right? Here, alpha will be not SSY. This will be SSE divided by the factor of safety for fatigue. This is given 1.5. And this is not given. But what I will start with to use the SSA, because SSM is 0, which is given on page 528, the value is 241. This is on page 528 for unpeened material. Sorry, unpeened material. So I use those 241 and 1.5. I got what is alpha, and I can calculate beta because I know the forces and the diameter. Once the C is known, I can got this one, 15.18. So once the C is known, we'll go over here and multiply by the wire diameter, and this is the mean coil diameter. It's straightforward, right? Nothing. The only thing what you need to watch in this case is this guy. That if it is a static case, you are using SSY. If it is a dynamic case, you are using SSE, which becomes SSA when the SSM is equal to 0. You know, this is the condition that we have in this problem, which this is 0. It ignores. Actually, I should write it is ignored. Now let's go to one and see that once I have the C, I can calculate the Berge-Strasser factor. Why I need Berge-Strasser factor? Because if you remember, you look at the equation for stress. So I'm going to use the Berge-Strasser factor to calculate the alternate stress, which I have used it over here. And so this is alternate stress, and this one over here is mean stress. Now you notice over here I'm not using F this value, because I already have over here an alternate and mean force. So I'm directly going to use alternate and mean force. Without this, I don't need this one. So my two stresses, one is this, one is this, one is alternate, one is mean. And I will also calculate the shut stress. And for the shut stress, I need, this is the equation for the shut force. The robust linearity is 0.15. Maximum force is 80. I got this is the shut force. And when I put the shut force, right, I got what we call as the shut stress, which is this one, which is 494.4. And remember, previous one, we already got the mean coil diameter is 42.5 mm. Now we will go and calculate the fatigue factor of safety. The fatigue factor of safety is, because of the absence of SSM, it is SSE and tau A. Now, since SSM is 0, ignored, I use the SSA divided by, this is the alternating stress, because I'm not now we are taking the mean is not considered over here, so my factor of safety comes 1.495, and this is what I am assuming it. What is the factor of safety at closure? This is the yield strength divided by shut stress. Yield strength is this and shut stress is this. I got this one, which is greater than equal to this condition. So this is acceptable as per general design constraint. Now remember, what is the value of over here for the C that we got? C came as 15.18, right? Does this satisfy this condition? The answer is that it does not satisfy this condition. No. But do we have a choice? No, because we want to do the all calculation using the wire diameter of 2.8. We are using the wire diameter of 2.8. So we proceed further. I know the wire diameter, I know the G, I know the mean coil diameter, I know the spring rate. I can calculate the number of coils. This is the number of active coils. Now look at it over here, 5.13, and let me go to this rule again of 1 quarter, means 0, 0.25, 0.5 and 0.7. So this is between 5.0 and 5.25. Now look at it where it is close. It is closer to this one. So I'm going to round off to this. So when I round off, I just got 5.25 coils. My total number of coils then, with the end conditions, I have to add 2 coils, that's 7.25 coils. Now then I can calculate what is the shut length. Shut length is wire diameter times the total coil, that's the shut length I got. The free length is LS plus FS over, okay, excuse me. My LS is 20.3, my shut force is 92, my K is 158, I add them, I got this is the free length. What is my outer diameter? D plus D is 45.3 and ID is 39.7 millimeter. I need to check for buckling, so I need to calculate this value. I know the D, I know the alpha. You can see what is the length of the critical length. this critical length is greater than L0. L0 is 78.5. So will the spring will buckle? Answer is no. The spring is buckle. Then I'm going to calculate over here the this is fundamental frequency. Over here. Okay. In order to calculate the fundamental frequency, because it is cutting, so I will just use the formula which is for the frequency. This is kg over this weight. This is the weight, this is W. And we have calculated the value of W. So we substitute the value of W here. This is the K. What is the value of the K? 1.58 Newton per millimeter. So I have converted into 1580 Newton per meter. So the value, let me write it again. So I will just go. So delete this and I will say it is 1.580 Newton per meter. What is the frequency that I got? Frequency I got 105.2 Hertz. And according to the condition, what I should have? That F should be 20 times. What is the applied frequency? Applied frequency was 5. So it should be greater than or equal to 100 Hertz, and it satisfies. Now you see over here, look at the value of the C. It is greater than D, 12, right? And this is the one that we have taken. So I have created an Excel sheet, and in that Excel sheet, I have substituted the formulas for C, the mean coil diameter, alternating stress, mean stress, shut stress, factor of safety against fatigue, factor of safety against shut, active coil, total number of coil, shut length, free length, outer diameter, inner diameter, critical length, and fundamental frequency. And this is for all of these diameters, wire diameters. From where these diameters came? This was given in the problem that the manufacturer has these diameter. Now I'm going to what I have created over here. This is my design map. Remember in the static case, I said we need to create a design map. And that's what we have created, a design map. Now we are going to make decisions. We are taking. So first, let me first delete. Why it's not? Okay. So I have my table back to the same. Okay. And I will start deleting. So first let me look at the condition. My first condition is that I am going to have the C greater than 12. So now I will change this to red color. So C greater than 12 means, let's look at it where my C is greater than 12. This is out. This is out. Cross. Okay. And that means these two columns will have a problem. Right? We'll see it later. That's just first, let me remove it. We'll put first the conditions and then we'll see. So this is done. N greater than 15 coils or less than 3. So I look at it, N, the coils. Okay, this is out. It is greater than 15, greater than 15, greater than 15, greater than 15, greater than 15. So all these are fine. This is taken care of. Shut length greater than 25 mm. So where is my shut length? I have my shut length is here, this row, right? So I will go in this row and check which one is greater. This shut length is out because it's larger. This shut length is also unacceptable. This is also unacceptable. This is unacceptable, 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 unacceptable. Only one is possible. So this is taken care of. Now the free length. By the way, this is not, I don't know, this is by mistake. This is L0, free length. So L0, this is greater than 100, right? This is greater than 100. This is greater than 100. This is greater than 100. Unacceptable. Now I'm going to check F, which is less than 100, right? Which is unacceptable. So this is unacceptable. This is unacceptable, less than 100, less than 100, less than 100, and these are fine. One last condition that I have to make sure that LO should be less than LO critical. So when I compare LO with LO critical, right, I know this is not acceptable because critical is a smaller. Here, same, critical is a smaller. Here, the same, critical is a smaller. Here, the same, critical is smaller. And now you look at it over here, then it is fine. If you just compare these two, this is fine. Did I apply all the rules? Yes. Now let's see which one are unacceptable. Now you look at it, all the columns have red. So this is, there are things which are out, right? And so let me go and say, okay, which one is going to give me now the problem? And let me, so this is out, this is out, this is out, this design is out, this design is out. Here is a serious violation. This design is out. This is a serious violation here, you see. This design is out. Now, do I have a choice? An answer is, according to this table, no, I don't have any choice. What are the problems? Right? I have two basically problems over here in this one. Let me go back to my green color. Okay, I go back to my green color. So why it is not going green color? And let me delete this. I delete this, and I delete this over here and this, and I'm going to delete this one also. Look first. The problem is here and here, two places. Here C is greater than 12, but close. So I will assume no buckling, because you know, if the C is greater than 12, it has a chance of buckling. I can take it acceptable. But what I will do this, here you look at this one. I need to go back to the designer and ask them, can I basically do changes in assembly? And that will basically that I will have a 0.35 mm. You see over here, it is just how much extra it is, 0.35 mm extra. So can I accommodate this? If I can accommodate this, then this will be my design. This is my design. This one, which is 2.6. But if I cannot, then I will go back to this 2.8 and I will say, okay, let's look at it over here. The only place the violation is this. Here is the violation. And I need to go back and very critically I need to check. Will it buckle? Right? And if it buckles, then I will have to find a solution. What I can do? I can take a rod and I put the spring outside this. So what I'm going to do? No buckling. Or I take a cylinder. So this is the wall of the cylinder. And inside I'm going to put the spring. So will it buckle? No. So I can take this design if I do follow for this particular design. If I choose to put over a rod or put inside a hole. That's how I'm going to accept the design. So if we go basically to the next one, that's what I have written, and you will see exactly the same thing that I told you is over here. So I don't have to repeat it. But as I said, I have used an Excel software and you can see page that this is from the Excel sheet. In each of these, I have these values, and here I have an equation. In each one of these places I have an equation. These are values, this is our equation. So this is an equation, this is an, okay, here. And I'm changing the D and I get all these parameters. So once I have made this Excel sheet, I go and change D, change it, and I get new values. And I do basically this and I get these conditions. And I generate the entire design. That concludes the first problem. I'm going to go faster in this problem. You see over here what we have to do is to design a second question, design helical compression spring against a dynamic load. Minimum load is this, maximum load is this, and deflection is here. Now here you notice that what has been given, that the load is given, minimum is 60 pound, the maximum is 150 pound. But what is the deflection over here is not given. What is the deflection at this load is not given. What is given that when it goes from 60 to 150, what is deflection? That deflection is delta y, which is given as how much? 1 inch. The forcing frequency is 1000 RPM, right? One shift operation per day for 10 years is required. That's the condition. It means I'm going to use this to calculate N, the life cycle. It suggests to use the music wire ASTM A228 with the pinning, so it's not a cheaper one, to obtain higher endurance strength. Also consider after set removed, means again it will be costly. Both things, pinning and after set removal, both of them are costly. So we will start. For this material, we know this is A and this is M, right? I have selected the gauge 4 from a steel wire. Again, appendix A to 8, but this is a steel wire. And what is the diameter that I have taken? 0.2707. So I got S ultimate and I got the ultimate strength in shear. I got the yield strength in shear. I have already the E and the G. Now, knowing the maximum force and minimum force, I can calculate alternating load and the mean load. This is alternating, this is mean. Going back to the previous procedure, remember second case of the what we call static problem. I am now assuming C. And when I assume C, C is known, D is also this, I will calculate it. The mean coil diameter, I have calculated what we call the shear correction factor, and I have calculated what is the initial stress, means at the minimum load. And how much is the minimum load? Minimum load is 60 pound. I have calculated the Bergstrasser factor. This is the alternating stress and this is the mean stress. The only difference is here we have what we call the FA and here we have this is FM. So one is 45, one is 105. This is 105 and this is equal to 45 pounds. Now here there is a slightly different procedure, and that procedure that I have used is taken from your book in chapter 6, and if you go on to page 3115, and it has a table for modified Goodman. Over there you will find a ratio R, which is defined as the alternating over mean. So I have calculated that R. And if I use the modified Goodman criteria, you remember that what I have written in the equation SSA on the previous slide here over SSE plus SSM divided by SUS is equal to 1. So what I'm going to get that from here is SSA over SSE is equal to 1 minus SSM divided by SUS, and if I just do the opposite, I will get this equation. SSA and SSM are given on page 528, and this is for peen, so I just have taken that material, but since we are solving a problem in FPS unit, I have converted these into from megapascal to PSI, the pounds per square inch. So knowing this, now I can calculate this, which is the SSE. This is SSE based on the same previous equation. What is the amplitude component? It is this one. Again, it is coming from figure on page what we call is 315, right? If I 315 and go to table 6.6, which is for modified Goodman criteria. So I can calculate the SSA, which is 43241 psi. I know the strength of the material. I know the alternate stress which I have calculated. What is my factor of safety? 1.56. Is it acceptable? Yes. Now I have to check the number of cycles. I should have done this before, and since I forgot it, so I said, but I have to do it because I need to make sure that n is greater than 10 raised to the power 6 so that we can use the endurance strength. So what is given? It is working at 1000 RPM. How many minutes per hour? 60 minutes per hour. How many shifts per day? One shift. In a day, usually what we have? In a day, we have 3 shifts of 8 hours each. So in other words, if they work excuse me, if they work for one shift, then I have 8 hours per day. How many days in a year? 365. How many years? 10 years. What is the value of n? 1752 million cycles, which is greater than 1 million cycle. So problem is an infinite life problem. So I don't have to do anything. I don't have to find fatigue strength. Endurance is fine. A spring rate, del F. How much is the force change? 150 minus 60. And already I have explained to you that the deflection is 1.0. It gives me K. If I know K, I can calculate N. It comes as 4.57. Now again, we look at it. 4.57 is between 4.75 and 4.50. And I have to go to the nearest 1.4. So this is the one. So this is the coil. Once I have the coil, the active coil, I can calculate the total number of coil based on the end condition. I can calculate the shut length. I can calculate the free length, right? I can calculate the inner diameter. I can calculate the outer diameter, and I can also calculate the critical length, which comes as 9.8. And look at it, that LO, which is how much we got LO? 3.27, and this is less than LO critical, and LO critical is how much? 9.8H. Will it buckle? No buckling. And that completes the problem. With this, now we can say that we have completed chapter 10 on mechanical spring. You need to practice. Over the weekend, I am going to send you the schedule for a take-home exam on a spring. So there will be, let me write it over here, there will be a take-home exam on a spring, and its weight is heavy. So please practice it, solve it. I will upload the I will tell you the date, and once the date is there, you are going to pick the exam, and then you will have a couple of hours to solve it and scan it and then upload it on the Moodle. You will get all the information about the exam. That will be on mechanical spring. It will be, the percentage of this will be somewhere between 10% to 15% of the grade. With this, let me conclude my lecture. I wish you good luck. Any questions on this, please do not hesitate to contact me. Thank you very much for listening with patience.